Hi everyone, my name's Alex. I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. Welcome to episode 3 of this 4-part video series on welding distortion. In this episode we'll take a look at flame straightening because the way I see it, mastering flame straightening is key to mastering welding distortion. So let's take a look. Flame straightening can be understood as producing on-purpose distortion, just by applying local heat. It is used to counteract welding distortion or distortion in general. This sample here, for example, is as welded, whereas this one was welded and then flame straightened. Also, we can use the process of flame straightening to give workpieces a slight deformation, such as on this sample here. This one is a rather extreme case and should give you an idea of the magnitude of deformation which we can induce by flame straightening. In this case it should rather be called flame deformation, but nevertheless I think you get the point. This particular sample shape is the product of a lot of consecutive passes. Usually flame straightening is employed to induce smaller deformations or corrections than on this one here. Flame straightening is based on the same mechanism which in the earlier episodes we called the primary mechanism of welding distortion. It works on almost all ductile metals and alloys. However, it works best on materials with low thermal conductivity and high thermal expansion. On the steels, for example, it works better than on aluminum alloys. I often heard that flame straightening is a hoax and doesn't work properly or controllably. This mistaken opinion might probably be due to some misleading textbook examples, of which I've seen a few. In these examples, the authors usually suggest applying a wedge-shaped heat to a workpiece like so. But if one follows these instructions, no notable deformation or straightening effect is achieved. Among other things, I'll try to show you why this is with the following experiments. In the first experiment, we will straighten this distorted T-joint. This is a pretty common case of welding distortion, which you've probably encountered before. The following pretty much also applies to a distorted T-joint of solid material, which may be long or short in this direction. The weld bead runs around this square tubing here. This joint was DCE and TIG welded freely, without clamping down and with no particular welding order. And the most notable distortion that resulted from welding is a V-shape of this bottom tube here. Just like so. And this V-shape amounts to, let's see, so that's approximately 1.3 millimeters. And if you check closely, you'll see that it's not a bow shape or anything else, because from episodes 1 and 2 we already know that the weld bead up here pinched the tube locally. That is right where the heated zones were, like so. There is also some distortion in this cross direction here due to these two weld beads. But let's assume we are not bothered by this one because the related deformations are small. So now we'll try to flame straighten the distorted tube here, just with the application of local heat. And in order to visualize this deformation of interest for you, let me rig this T-joint with this indicator here. And since we know that the V-shape distortion amounts to 1.3 millimeters, let me set the indicator to that amount. Should do it. And I'll try to straighten the tube so that the indicator in the end shows 0, at which point the tube should be fairly straight again. From episodes 1 and 2 we know that by applying local heat we can create a local pinching effect. And in order to get this tube straight, consequently we should apply local heat right here, opposite to the weld beads which distorted the tube in the first place. Let's first try to do this the textbook way and apply a heat wedge like so. Keep an eye on the indicator and remember we started at 1.3 millimeters. So even though we heated a fairly large portion to an orange red up here, this obviously didn't work in one pass. So what to do next to reach 0? From episode 1 we already know that we may heat the same spot again to create even more local thickening and pinching. So we've gained another 0.2 of a millimeter with the second pass, way less than with the first one. The first one was approximately 0.6 of a millimeter. The difference between the first and the second pass was not so much size or location of the heated spot, but more bumping over the residual stress pattern that was left from welding. From episode 1 we already know why our gain in the second pass was so low, judged by the fact that the heated spot in the second pass was fairly large. Recall the heated spot experiment where we placed one spot close to the sheet's edge. Not much thickening and therefore pinching occurred because the heated spot's expansion wasn't constrained much, and hence the cake didn't rise, so to say. A similar thing happened here. Since we evenly heated the upper part here, it expanded and the tube bent almost like if it had a hinge back here. Nothing much constrained the expansion of the heated zone in this direction, or rather in this direction, in which we would like to pinch the tube. So obviously just heating this area here is not the best way to straighten the tube. Now let's apply the heat a little more smartly in a way which constrains the heated zone expansion in this direction better than before. There are several ways to do this, all of which have in common that part of the area up here remains cold. Let's try heating just the corners because they take the heat most quickly. The temperature and size of the heated spot as well as the amount of constraining decide about how much pinching we get. It is rather typical for flame straightening that a few runs are necessary to obtain the desired shape. Very important for flame straightening to work is to heat up as quickly as possible to ensure high temperature differences in the workpiece. If instead we do heat it slowly and/or by using a small torch, the heat will spread out and temperature differences in the workpiece will decrease. Or you could say heating slowly gives a similar situation as preheating does, of which we know that it reduces the thickening and pinching effect. So you see, the third pass gave us approximately the same gain as the second one, even though we applied just very tiny heated spots to the two corners. And this gives us a good feeling of how large a heated spot to apply in the next pass in order to hopefully reach zero. Alright, so let's try to get rid of the last 0.2 of a millimeter of distortion. Sorry I didn't nail it to zero, but 3/4 of a tenth of a millimeter is a fair number, I think, for a straightened welded joint. So let's keep in mind that there are smart and not so smart ways to apply the heated spot. The smart ways make use of very tiny and small heated spots, which are well constrained by the workpiece itself and give a good straightening effect. We can speed up the process of flame straightening this joint by constraining the heated zone expansion even more. This can be done by stiffening the workpiece, for example by clamping it down or by clamping something rigid onto it. Let's try doing it this way. Hereby we constrain bending of this tube as we heat it quite a lot. Because if we do it this way and clamp it down this way, the table is much more rigid than the workpiece. But first, let's check the distortion of this one. And this one is also roughly 1.3 of a millimeter. And in order to show you that we do not bend the tube by clamping it to the table, let me loosen it again and recheck the distortion. And the distortion is still 1.3 of a millimeter. So clamping it to the table does not bend it back enough in order to get rid of the distortion or any part of the distortion. And you see, I got it in one run. I probably did over straighten it, but I guess you get the point. The water cooling I used does not alter anything from a material point of view with this mild steel here. Cooling is just for speeding up the work and to inhibit that our workpiece gradually preheats. Remember, preheating reduces the pinching effect very notably. Also, we have to check the improvements of our workpiece geometry. But this only makes sense with a workpiece that has entirely equalized temperature, which practically means it's entirely cooled. Here usually the question arises if flame straightening does load the workpiece with more residual stresses than welding alone does. Well, it is difficult to give a general answer to this question. But from episodes 1 and 2 we know that residual stresses from welding are significant compared with the material's yield strength anyway. So let me try to answer this question as follows. Flame straightening definitely changes the workpiece's residual stress pattern. But with the small strains involved here, I'm sure to say that the maximum residual stresses in the workpiece won't become much higher by flame straightening compared with what they amount to due to welding. The question if more of the workpiece's volume is loaded with high residual stresses does depend on the case at hand and can't be answered in general. Also, we have to keep in mind that with almost all welded designs, good workpiece geometry is a primary matter, whereas residual stresses usually must be considered secondary. The case I demonstrated here is a case of quite thin metal, with wall thicknesses being 2 mm or roughly 80 thousandths of an inch here. A case where we can safely assume that the heated zones penetrate the wall. With notably thicker material, it's furthermore possible to create pinching just on one side of the part. For example, when you have to straighten a thick plate. The principles are the same as with our square tubing, except that the heated spot does not penetrate all the way through the workpiece or wall. Like so. Don't get fooled by the discoloration pattern here. The discoloration pattern is not what primary counts. What primary counts is the red hot nugget in case of the steels. Let me note here that the thicker the material or section, the easier flame straightening becomes. It also becomes easier the more distortion susceptible the material is. That is, the lower the material's heat conductivity and the higher the material's thermal expansion. Non-magnetic stainless steels, for example, are more distortion susceptible than magnetic mild steel, and therefore easier to flame straighten. Now finally, let me show you an example which is quite difficult to flame straighten. This is a T-joint of thin mild steel. The sheet's thicknesses are 1 mm or roughly 40 thousandths of an inch. This joint is DCEN TIG welded freely without clamping it to the table or anywhere else. Also, I didn't back purge it here because this sample is not intended to demonstrate strength, but rather it's intended to demonstrate distortion, the latter of which you can readily see. From the foregoing discussion now, we know that the weld bead primarily caused pinching along this direction here, because the heated spot when I welded it was much larger in this direction than it was in this direction. So for straightening the base sheet here, we obviously need to pinch it by heating the outer zones here and there. So let's give that a try. But obviously if we do this, you see that distortion becomes worse. This is because of a problem referred to as thermally induced buckling. The rigidity of our base sheet here, out of plane, is so low that it buckles under the additional compressive stress which we create by applying local heat. This is a common problem in welding applications with mostly flat and thin-walled segments, for example in case of bus or train chassis. A technique which helps here is to stiffen our workpiece out of plane direction, like so, by clamping on some bar stock. Forgive my clumsiness. The stiffening now should prevent buckling and allow for successful pinching at the right place. Let's give it a try. I'm gonna just quickly cool this. So even though this is just the first pass and this workpiece is surely not fully straightened yet, I think you get the point and you get the idea of how one can help himself in a case like this. I've seen quite sophisticated rigs for such work on thin sheet metal, such as plates that are clamped to the workpiece by vacuum and have many holes to give access to the workpiece for the torch. Well, so far for episode 3 of this video series. In the next and final episode we'll take a look at some techniques that help us to influence distortion right during welding. Thank you very much for your interest in this video. I appreciate your time. All the best for your welding projects and thank you!